Earth exists in a hostile environment. Our planet is constantly bombarded by dangerous solar radiation that could strip away our atmosphere and make life impossible. The sun continuously emits a stream of charged particles and electromagnetic radiation known as solar wind. This radiation travels through space at incredible speeds, reaching Earth in just a few days. Without protection, this solar radiation would gradually strip away Earth's atmosphere. Just like what happened to Mars billions of years ago, our planet would become a barren, lifeless world. Fortunately, Earth has a powerful invisible shield protecting us. This shield is Earth's magnetic field, also known as the geomagnetic field. It's generated deep within our planet's core. This magnetic field extends far into space, creating a protective bubble around our planet called the magnetosphere. It acts like an invisible force field, deflecting most of the harmful solar particles away from Earth. The magnetic field is so effective that it allows Earth to maintain its atmosphere and protective ozone layer. This creates the perfect conditions for liquid water to exist and for life to flourish on our planet. In this video series, we will explore how Earth's magnetic field is generated deep within our planet, how it creates the magnetosphere, and how this invisible shield protects us from the constant threat of solar radiation. Understanding Earth's magnetic shield is crucial for appreciating how our planet supports life and what challenges we might face as this protective field changes over time. Deep within Earth lies a powerful engine that creates our planet's protective magnetic field. This engine is called the geodynamo, and understanding how it works reveals one of nature's most remarkable processes. Earth's core consists of two distinct layers. The inner core is solid iron and nickel, while the outer core contains the same metals in liquid form due to intense heat and pressure. The geodynamo process begins with Earth's rotation and the intense heat from the core. This creates convection currents in the liquid outer core, where molten iron and nickel flow in complex patterns. As this molten metal moves, it carries electric charges with it. The movement of these electric charges creates electric currents throughout the outer core. These electric currents flowing through the liquid outer core generate magnetic fields. According to the laws of electromagnetism, moving electric charges always create magnetic fields around them. As the electric currents intensify, the magnetic field grows stronger and extends far beyond Earth's surface, creating the magnetosphere that protects our planet. This geodynamo process has been operating for billions of years, continuously generating the magnetic field that shields Earth from harmful solar radiation and cosmic particles. The magnetic field surrounding Earth creates a vast protective region called the magnetosphere. This invisible shield extends far into space, forming our planet's first line of defense against harmful solar radiation. The sun continuously emits a stream of charged particles called the solar wind. These high-energy particles travel through space at speeds of hundreds of kilometers per second, carrying enough energy to strip away planetary atmospheres. When the solar wind encounters Earth's magnetic field, it creates the magnetosphere, a bubble-like region that deflects most of these dangerous particles away from our planet. The magnetosphere acts like an invisible force field, protecting Earth's atmosphere and surface. The magnetosphere has a distinctive asymmetric shape. On the day side facing the sun, the solar wind compresses the magnetosphere, creating a blunt, rounded boundary. On the night side, the magnetosphere stretches out into a long tail that can extend for millions of kilometers into space. The night side tail forms because the solar wind flows around the magnetosphere like water around a rock in a stream. This tail structure is crucial for storing and releasing magnetic energy, and it plays a key role in space weather phenomena that affect Earth. Without the magnetosphere, Earth would be constantly bombarded by harmful solar radiation. This protective magnetic bubble is essential for maintaining our atmosphere and creating the stable conditions necessary for life to thrive on our planet. Earth's magnetic field acts as an invisible shield, deflecting the vast majority of harmful solar particles before they can reach our planet's surface or atmosphere. The magnetosphere forms a protective bubble around Earth. When the solar wind, a stream of charged particles from the sun, encounters this magnetic barrier, most particles are deflected away, never reaching Earth's atmosphere. Solar wind particles travel at incredible speeds of 400 to 800 kilometers per second. Without magnetic protection, these high-energy particles would gradually strip away Earth's atmosphere, just as happened to Mars billions of years ago. But Earth's magnetic field deflects these particles, bending their paths around our planet. The particles follow curved trajectories, flowing around the magnetosphere like water around a rock in a stream. By deflecting solar particles, the magnetic field performs several critical functions. It prevents the gradual stripping of our atmosphere, protects the ozone layer that blocks harmful ultraviolet radiation, and maintains the conditions necessary for life on Earth's surface. The strength of Earth's magnetic field determines how effectively it can deflect solar radiation. A stronger field provides better protection, while a weaker field allows more particles to penetrate closer to Earth. This deflection mechanism is fundamental to Earth's habitability. Without our magnetic shield continuously deflecting solar radiation, our planet would gradually lose its atmosphere and become uninhabitable, much like Mars did billions of years ago. Not all solar radiation is deflected by Earth's magnetic field. The radiation that does penetrate our magnetosphere is managed through two remarkable phenomena: the Van Allen belts and auroras. The Van Allen belts are two donut-shaped zones of intense radiation that surround Earth. These belts act like cosmic prison cells, trapping harmful charged particles from the solar wind and cosmic rays. When solar particles approach Earth, many become trapped in these radiation belts. The particles spiral along magnetic field lines, bouncing back and forth between the north and south poles, effectively contained within these zones. However, Earth's magnetic field has openings at the poles. Some solar wind particles can penetrate through these polar cusps, following magnetic field lines down toward Earth's atmosphere. When these charged particles collide with gases in Earth's upper atmosphere, they create the spectacular light displays we call auroras, or the northern and southern lights. These natural light shows are not just beautiful, they represent our planet's magnetic field in action, channeling potentially harmful radiation into harmless displays of light. Together, the Van Allen belts and auroras demonstrate how Earth's magnetic field manages the solar radiation that penetrates our magnetosphere, either trapping it safely away from our planet's surface or converting it into beautiful natural phenomena. Earth's magnetic field is not constant. Scientific studies reveal that our protective magnetic shield is gradually weakening, and the magnetic poles are continuously moving across the planet's surface. Over the past 200 years, Earth's magnetic field has weakened by approximately 9% on a global average. This represents a decline rate of about 6% per century. The weakening is not uniform across the globe. The South Atlantic anomaly represents a particularly weak spot in the magnetic field, located over South America and the Southern Atlantic Ocean. This region allows charged particles to penetrate closer to Earth's surface than normal. In addition to weakening, Earth's magnetic field is also shifting. The magnetic poles wander continuously across the planet's surface. The North Magnetic Pole has moved approximately 1,300 kilometers in the last century alone. Scientists continuously monitor these changes using satellites, ground-based observatories, and sophisticated data analysis. This monitoring reveals that the magnetic field strength is decreasing at about 6% per century. The magnetic poles are moving continuously, and regions like the South Atlantic anomaly are expanding. The South Atlantic anomaly, or SAA, is a region where Earth's magnetic field is unusually weak. Located over South America and the Southern Atlantic Ocean, this area represents a significant vulnerability in our planet's magnetic shield. In this region, the magnetic field strength is significantly reduced compared to other areas of Earth. While the global average field strength is about 30 microteslas, the SAA can have field strengths as low as 22 microteslas. This weakened magnetic field allows charged particles from space to penetrate much closer to Earth's surface than normal. These particles, which would typically be deflected at higher altitudes, can now reach down to about 200 kilometers above the surface. Now let's examine geomagnetic storms, which occur when variations in solar wind disturb Earth's magnetosphere. These storms can have dramatic effects on our technology and infrastructure. Geomagnetic storms occur when solar wind carries enhanced magnetic fields that interact with Earth's magnetosphere. These storms can last for several days and have wide-ranging impacts on modern technology. The effects of geomagnetic storms are far-reaching. They can disrupt GPS navigation systems, cause power grid failures affecting millions of people, damage expensive satellites, interrupt radio communications, and pose serious radiation risks to astronauts in space. During severe geomagnetic storms, power grids can experience cascading failures as induced currents overload transformers. Satellites may suffer permanent damage from increased radiation, and the economic impact can reach billions of dollars. The South Atlantic anomaly and geomagnetic storms represent ongoing challenges as our society becomes increasingly dependent on technology. Understanding and monitoring these phenomena is essential for protecting our infrastructure and ensuring the safety of space missions. Earth's magnetic field is not static. It has undergone dramatic changes throughout our planet's history, and scientists are working to understand what the future holds for our magnetic shield. Throughout Earth's history, the magnetic field has undergone complete reversals, where the north and south magnetic poles switch positions. During normal polarity, the magnetic north pole points toward geographic north, but during reversed polarity, it points toward geographic south. The last magnetic reversal occurred approximately 780,000 years ago. On average, reversals happen every 200,000 to 300,000 years, which means we may be overdue for the next one. However, the timing is highly irregular and difficult to predict. Several signs suggest that a magnetic reversal might be approaching. The magnetic field has been weakening at a rate of about 6% per century. The magnetic poles are wandering faster than usual, and weak spots like the South Atlantic anomaly are expanding. Scientists are actively engaged in space weather research, developing sophisticated models to forecast solar activity and its impact on Earth. Organizations like NOAA provide real-time monitoring and early warning systems to help mitigate potential problems from solar events. The ocean floor provides a detailed record of magnetic reversals. As new oceanic crust forms at mid-ocean ridges, the cooling rock records the current magnetic field direction, creating alternating stripes of normal and reversed polarity that serve as a timeline of Earth's magnetic history. While we cannot prevent magnetic reversals, we can prepare for their effects. Scientists are working on protecting satellites, shielding power grids, and developing backup communication systems. Understanding space weather helps us build resilience against solar storms and potential magnetic field disruptions. The future of Earth's magnetic field remains uncertain, but through continued research and preparation, we can better understand and adapt to the changes that lie ahead. Our magnetic shield has protected life on Earth for billions of years, and understanding its behavior is crucial for our technological civilization.